I want to finish talking today about the future expansion of the universe. We talked about the fact last time that if we try to add up all the matter in the universe to see if there's enough gravitational pull to pull everything back together, the answer seems to be no. We also saw that if we look more carefully and try to really carefully measure the masses of galaxies by measuring their rotation, we find that they're heavier than they appear like they should be. Their mass is more than the mass of a few 100 billion stars. This gives rise to the problem of dark matter. We believe that galaxies and clusters of galaxies contain some kind of matter that we're not seeing, matter that doesn't give off much light or enough light that we can see it in our telescopes. This is an unanswered question in physics and astronomy. What is the dark matter? I should mention really quickly that there's another explanation. Just because we should be honest in science that there are multiple possibilities when we observe something we don't expect. How do we come up with the idea of dark matter? We look at galaxies, we measure their rotation, we find that they're rotating pretty fast, and we use the law of gravity to figure out how much mass they have, and that mass is big. And we conclude that there's mass there that we're not seeing. But there could be another explanation, which is that at galactic scales of hundreds of thousands of light years, Newton's law of gravity or the laws of general relativity aren't right. That our theories of gravity are only right on small scales, a few light years, tens of light years, 1,000 light years, but they get more and more off as you get out to hundreds of thousands of light years. And they give predictions that are wrong. There are scientists seriously investigating this possibility. It's called modified Newtonian gravity models. But Einstein's theory of general relativity provides such an effective description of gravity that explains so many things so precisely that it's difficult to imagine that it's just a little bit off. So it's possible, and we're not neglecting that possibility. We are investigating that possibility. But a far more likely possibility, if you know the term Occam's razor, which is this principle in science that you choose the simplest explanation. It's a much simpler explanation that there's just some matter we're not seeing than that the whole law of gravity is wrong. So that's what we do. That's what we assume. But this is an unanswered question, and the verdict is still out. And I ended with, well, instead of just adding up mass in the universe and asking, is there enough gravity to pull everything back together? Can't we just look at the universe and see if it's slowing down or not? After all, when we look at very distant galaxies, we are looking at them in the past. So can we measure the slowdown of the Big Bang expansion directly by looking at very distant galaxies and seeing if they're moving faster or slower than we would expect? The answer is yes, if you can make very accurate measurements of the distances and speeds of very distant galaxies. This was not possible until, say, the late 1990s or so. So this is very new information. We talked about the fact that Hubble's law, a uniform expansion of the universe, predicts a straight line relationship between velocity and distance. That formula, velocity equals a constant times distance, is called Hubble's law. That constant is called Hubble's constant. But what if the expansion wasn't uniform? What if the expansion was speeding up or slowing down? What would that look like? It's a little bit counterintuitive because we have to combine the fact that we're looking at how the speed changes over time with the fact that we are looking back in time when we look at those very distant galaxies. So suppose the expansion of the universe was slowing down as we expect it to be. That means when we look back into the past at very distant galaxies, they should be moving faster than we would expect because the universe has slowed down since then. So the expansion of the universe that is slowing down would look like this. As you get out to very distant galaxies, they are moving faster than Hubble's law would predict because that's what they were doing in the past. We're looking at them a long time ago. So if the graph does this, that means the universe has slowed down since then. It's super counterintuitive, and I have to explain it to myself really clearly every time. Because I see a graph that does that, I think, oh, that's something speeding up. No, because these galaxies, we are looking at their velocity in the past. So if they were going faster than we would expect in the past, that means since then, the expansion has slowed down. So in the 90s, we've got the Hubble Space Telescope at our disposal. We can look at further and further and further and more distant and dim galaxies. We can measure the brightness of the galaxies and the brightness of things like supernovas happening in the galaxies. And we can measure the distance. And we can add points to our graph of the speed of galaxies as a function of their distance. We can extend this graph to dimmer and dimmer and further galaxies. And what we got was not what we expected to get. We expected to get either Hubble's law or a slowdown indicating that the gravitational pull of the universe on itself was slowing down that expansion. What we got instead was this. Very distant galaxies are moving away from us more slowly than Hubble's law would predict. That means that since that time in the past, the universe has sped up. The expansion of the universe seems to be not only not slowing down and not slowing down enough to close the universe and stop the Big Bang expansion. The expansion of the universe seems to be speeding up. What? Why? Why would that happen? If something's speeding up, that means there has to be something pushing it. What could be pushing the galaxies and making them speed up more and more? This is an answer that no one was looking for and no one wanted, to tell you the truth. For about 10 years, maybe even longer, 10, 12 years, when I got to this part of my astronomy class, I would say, look, guys, this is new stuff. It's 2007 now, 2008. This was discovered in 1999. We don't need to pay a whole lot of attention to it until astronomers have sorted out and we're sure that this data is reliable. Well, that was a long time ago. It's now 2022, and this data is not going away. And so I stopped saying that. I stopped saying, let's just ignore this until we're sure. Well, we're sure. That's not going anywhere. It appears that all our data suggests that the expansion of the universe is accelerating, not slowing down, which means that the future of the universe will be an infinite expansion, that the universe will keep speeding up and speeding up. The universe will get bigger and bigger and bigger. And the rate at which the universe expands will get faster and faster and faster. Okay. So this is an option we hadn't considered. We considered two options. The universe keeps expanding at the same rate, or a slightly slowing down rate, and keeps expanding forever, or the expansion reverses and collapses again in a big crunch. We did not consider the possibility that the expansion accelerates and speeds up. So scientists had to go back and think about, well, what this means. What does this mean for the future of the universe? Well, it's a pretty bleak picture of the future of the universe, actually. Say what you will about the big crunch, at least it was exciting. Like everything comes back together and gets hot and dense and returns to the initial state of the Big Bang fireball. In this new picture of the universe, everything just gets further and further apart. Galaxies get further and further away until we won't be able to see any other galaxies in the distant future because they'll be too far away and their light will be too redshifted to even see. And we're talking about trillions of years in the future, but still, at some distant point in the future, the Milky Way, if you're in the Milky Way, you won't be able to see those other galaxies at all. How do we explain this acceleration? If we go back to this description of Albert Einstein's of gravity as a curvature of space and time, we explain why the Earth has gravity by thinking of the Earth like a ball on a trampoline. A ball on a trampoline changes the shape of the trampoline. So if you take a trampoline and put a bowling ball on it. It changes the shape of the trampoline such that if I put a golf ball on that trampoline, it will roll towards the bowling ball, right? It follows the shape of the trampoline. The shape of the trampoline has been curved by mass. That curvature of space is gravity. If we think about putting mass on a trampoline or putting energy on a trampoline, that would bend it down. The way to think about the energy of the whole universe is to imagine a trampoline with snow on it, right? You've got a trampoline outside, it snows 6 inches. The whole trampoline would sag downwards. And anything that you put on that trampoline would roll towards the center. So that's kind of how we imagine the universe. There's mass and energy everywhere that curves space inward that will eventually cause everything to slide back into the center. And that picture would look something like this. That's not what's happening. What's happening is everything is accelerating away from everything else. How would you do that? Well, the way you would do that is instead of imagining a trampoline with snow on it, causing a negative curvature, pushing it down, imagine a trampoline and you put a bunch of helium balloons underneath of it. And you keep putting helium balloons underneath of it until the trampoline curves the other way. And then if you put 2 balls on the trampoline, what would they do? They would roll away from each other. So the way we imagine this acceleration of the expansion of the universe to be caused is that everywhere in space, there is a little bit of energy that causes not a positive curvature like mass does, but a negative curvature. And if there's enough space between things, all of this accumulated negative curvature pushes those things apart. And the name we give to this little bit of energy that exists everywhere in space is dark energy. I don't know why they picked a name that was so similar to dark matter, which means something completely different. Dark matter and dark energy have nothing to do with one another. It is a very unfortunate duo of terms. Dark matter is regular old matter with positive mass that exists in galaxies that causes them to have more mass than we think they should. Dark energy is energy that exists at every point in empty space that causes empty space itself to have a curvature that tends to push things in the universe away from one another. We don't notice dark energy in the solar system or in the galaxy because there's not enough space between things in the solar system or the galaxy for this dark energy push to add up to anything measurable. But if you get to the distances between galaxies, millions, tens of millions, billions of light years, 1 billion light years of dark energy exerts enough push to push those galaxies apart. Are we stuck with dark energy? Nobody asked for it. Do we have explanations for why there would be energy in empty space? Not really yet. So we can go ahead and file this away as another unanswered question in physics and astronomy, a question about how the universe works that we simply do not have the answer to. And again, that's okay. Unanswered questions are the raw material for science. So we shouldn't be troubled by it, but we should be aware of the fact that our current situation in astronomy is that we've got these 2 big invisible components of the universe that we don't really know what they are or why they exist. It's worth mentioning really quickly that dark energy is not a brand new idea. That Albert Einstein, when he wrote his original field equations for general relativity that explained how mass and energy curve space, if you look at this formula, do I explain what the things are? Yeah. The symbol on the left-hand side, G sub alpha beta, is the metric of space, the curvature of space. 8 pi, you know what pi is. G is Newton's gravitational constant. C is the speed of light. And this T alpha beta is the stress energy tensor. It's the distribution of matter and energy in space. So Einstein's field equation says, if you have this distribution of mass and energy in space, you will get this curvature of space. It's an equation that looks fairly simple. This is actually the alpha and beta are subscripts indicating that T and G are actually a 4-dimensional matrix something called a tensor. So this is actually 16 differential equations written in a very compact form. It's actually much more complicated than it looks. It's not just an algebraic equation. But it expresses a simple idea, which is a certain amount of matter and energy distributed in space in a certain way creates a certain curvature of that space. Well, when Einstein wrote down these field equations, he quickly realized that if you had an empty space with nothing in it, just a universe with no atoms, no light, it would be static. But as soon as you put one thing in that universe, a single electron, a proton, a photon of light, that would cause a curvature of space, and that would cause that universe to collapse. Obviously, our universe isn't collapsing, so that seemed wrong. So he had to fix his equations. Remember, Einstein developed special relativity in 1905, general relativity around 1915 to 1917-ish. We didn't discover the universe was expanding until the late 1920s, early 1930s. We didn't fully accept it until the 1960s. So, as far as Einstein knew, he lived in a universe that was static. There was no Big Bang. There was no expansion of the universe. As far as Einstein knew, and as far as people knew in the early part of the 20th century, the universe had always pretty much looked the way it looked. So what Einstein did was he just added a term to his equation. Hold on, I've got a couple of images here explaining that the universe would collapse without this extra term. And he added a term that just provided an outward force that kept the space-time from collapsing in on itself. We called this term at the time the cosmological constant. Cosmological because it is a little bit of negative energy on the right-hand side of the equation that keeps the universe from collapsing in on itself. Einstein once called the cosmological constant his greatest blunder, his greatest mistake. Why? Because it was discovered about a decade and a half later, that the universe was expanding. You don't need a cosmological constant to keep the universe from collapsing. The Big Bang took care of that. The Big Bang, whatever it was that precipitated this event, pushed everything in the universe away from itself. And so you don't need the cosmological constant anymore. So we threw it away after we accepted that the universe was expanding. We didn't need it anymore until the 1990s and early 2000s, where we said, well, wait a minute. Maybe we do need the cosmological constant, because not only is the universe expanding, its expansion is accelerating, and we need to explain that acceleration with some kind of outward force. Dark energy appears in this equation in exactly the same place as Einstein's cosmological constant. It performs the same job. It's a negative energy in space-time that pushes matter apart if there's enough space in between there. So maybe it wasn't a mistake. Maybe Einstein realized, well, maybe he didn't realize it, but Einstein's notion that a negative energy term on the right-hand side of the equation would push the universe apart winds up being something that we needed a century later after Einstein. Let's go ahead and stop that there. So what have we discovered in the past two lectures? We've discovered two important things. One, when we look at galaxies themselves, they seem to have stuff in them that we're not seeing, that their gravitational pull on themselves is bigger than just the gravitational pull of a few 100 billion stars. The stuff we have identified as responsible for that is dark matter. We've also seen that if we look at distant galaxies and their motion away from one another, that motion seems to be accelerating, not just moving apart at a constant speed, but moving apart faster and faster and faster over time. We attribute that motion to something called dark energy, an energy in empty space that exerts an outward push on the universe and causes its expansion to accelerate. Dark matter is an idea that dates back to, say, the 1970s, 1980s. Dark energy is an idea that dates back barely 20 years. We are still figuring these things out. And that is interesting, I think. So what we want to talk about in our very last lecture, and it's going to be kind of a rambling grab bag, I would expect. And I'll post this on Monday, is what are, in my personal opinion, the most important unanswered questions in astronomy right now. And what hope do we have of answering them? What would we have to do in order to answer these questions once and for all? So it might be a long one. It might be a rambly one. But it is, I think, the end point of a class like this, which is not just about what we know about astronomy, but what are the questions that are currently driving the field? And what drives scientific progress, as I've said a few times now, is unanswered questions. So on Monday, we'll talk about what those are.